Okay, so in this video we're going to be introducing the idea of a continuous random variable. So we've already talked about discrete random variables. So discrete data is data that takes distinct, usually integer values. And a nice distinction is that when we're talking about discrete variables, we're often talking about the number of something. The number of times this happens, the number of times I toss a head when I toss a coin, the number of times I roll a 6, the number of people who contract a certain disease, whatever, okay? Continuous data is data that can take any value, or any value within a range, but you know, could be to 25,000 decimal places if you had the ability to measure to that accuracy. So where distinct data is often, or distinct distributions often come from countable quantities, continuous is often from measurable quantities: time, weight, height, length, distance, whatever. Okay, so there's no, essentially, when you're talking about a measurable quantity, and a continuous variable, there's no limit to the level of accuracy to which a continuous random variable can be measured. So, for example, if we're measuring a person's weight in kilograms, we're only restricted by the level of accuracy of the measuring instrument being used. So if we measure a person's weight as 70 kilograms, it may actually be 69.8 kilograms or 70.1 kilograms. But if your scales only give the measurement to the nearest kilogram, then you'll state that person's weight as 70 kilograms. But they probably don't weigh exactly 70 kilograms. And then even if we were able to get a set of scales that go to 1 decimal place, so let's say the scales now tell us that person weighs 69.8 kilograms. Well, actually they may be 69.82 kilograms or 68.97 kilograms, okay? Sorry, 69.78 kilograms, for example. So we could go on like this forever. So then if we were to have a set of scales that measured to 2 decimal places, you might say, okay, this person weighs 69.83 kilograms. But then again, that it just means that that's their weight to 2 decimal places. And we could go on and on forever. So unless we had a set of scales that could measure to infinitely many decimal places, it is impossible to actually measure a person's weight exactly. And so therefore, since it's not ever possible to measure a weight exactly, the probability of a person weighing a particular weight is actually 0. So the probability that someone weighs 70 kilograms, probability that W equals 70, for example, is equal to 0. We would always, in a continuous random variable, we would always talk about an interval. So we would look at the probability that someone's weight is between 69.9 kilograms and 70.1 kilograms. We would look at that probability, or a narrower interval. But to say that someone weighs an exact value, that probability is 0. So, as I said, for this reason, continuous random variables need to be grouped. So let's suppose that we measure the weights of a large group of randomly selected people and construct a histogram. So let's say this is our histogram. So the probability that someone weighs between 82.5 kilograms and 83.5 kilograms could be found by dividing this shaded region here by the total area of the histogram. Okay, and that would give us the probability that someone is within that particular category. So then if we were to instead rescale the histogram so that the total area of the histogram is 1. So for example, rather than this measuring frequencies, it's now going to essentially measure proportion. So let's say that that was 20 people out of, I don't know, 100 people. It's not that, but I'm just making it up. We would instead rescale the histogram, so that's now 0.2, okay, which would then mean all the total area ends up, actually no, that would give us a maximum, yeah, so that would work. So, so the total area of the histogram adds up to 1. Is 1. And so therefore we wouldn't need to divide the shaded area by the total area, because if the total area is 1, then it would just be the shaded area that gives the probability. Okay, so so we want to think about this idea of making sure that the total area is 1. So then if we were to increase the sample size so that we can decrease the width of the class intervals. So if instead of having the weights of 100 people forming this histogram, we now have the weights of 1,000 people or 10,000 people or 100,000 people. And what that allows us to do is use smaller class intervals, and hence we can create smaller bars, you know, each with so we're sort of grouping the data more precisely. And essentially, the more we do that, the larger and larger and larger we make the sample size, the smaller and smaller and smaller that allows us to make the class intervals, the smoother and smoother and smoother this histogram is going to get. And ultimately, the bars get narrower and narrower and narrower until the histogram can be modelled by a smooth curve. Okay, so this red curve here being used to model this histogram. And that curve is called a probability density function. And it's used to describe the probability distribution of a continuous random variable. So when we have a continuous random variable, our probability distribution won't be described as a table of values because there are infinitely many possible values that the variable can take. So unlike a discrete distribution where we roll the dice, we toss a coin 5 times and we're interested in how many heads we can get, well, there are only 6 possible outcomes. We get 0, 1, 2, 3 or 5 heads, and then we can calculate specific probabilities for those 6 outcomes and draw up a table. If we have a continuous random variable, the data can take any particular value. So if we're looking at weights of people, it could be anything, and so we can't construct a table where for every value we calculate a probability. And in fact, we've just determined that it's actually not possible to calculate a probability for a specific value. So the distribution of a continuous random variable won't be a table like we saw with discrete random variables. It will be a smooth curve, which we call a probability density function, or a PDF for short. So now we have our probability distribution represented by a smooth curve, which in this case is f of w, a function of the weights. It's actually a function of the probability of the weights, but that's okay. So remember, we rescaled our histogram to make sure that the total area was 1, and then we've fitted it with a smooth curve. And so we now have a smooth curve under which the total area is 1. And so therefore, if I want to find, I now know that the total area under this whole entire curve is 1, okay? And so if I want to find the probability of someone weighing between here and here, I need that bit of area divided by the total area, but the total area is 1, so I just need that bit of area. And so this becomes an integration problem. I need to integrate this probability density function from 82.5 to 83.5 if I want to work out the probability of someone weighing between 82.5 kilograms and 83.5 kilograms. So in general, for a continuous random variable, x with the probability density function f, the probability that x is between a and b will be equal to the integral from a to b of f of x. So a function f of x is only a probability density function if it has the following properties. F of x must be greater than 0 for all x. Okay, so the entire probability density function has to sit above the x-axis. Okay, we can't have negative probabilities, so it can't go under here. The second thing is the total area. So if we were to integrate f of x from negative infinity to positive infinity, the total area under the curve has to equal 1, okay? Or else it's not a probability density function. The other thing we want to recall before we move into some examples is that, remember, the probability of a continuous random variable being equal to a particular value is 0. And so this means that if we want to find the probability that x is between a and b, that's the same as including a, it's the same as including b, and it's the same as including both a and b. So all of these things will be equal to the integral from a to b of f of x dx. Okay, they're all going to be the same thing, regardless of whether the endpoints are both included, one included, neither included. Okay, it's going to be exactly the same. Okay, let's work through some examples. Consider f of x equals, and we've got this function here. So it is a cubic function between 0 and 1, and it is 0 otherwise. Often PDFs will be hybrid functions or piecewise functions. Sketch the graph of f of x and show that f is a probability density function. Okay, so we want to sketch the graph, so we want to think about this cubic. It's got x-intercepts at 0 and 1 using the null factor law. The squared here tells me that there's a turning point at 0. So essentially, it's going to be doing this. Okay, so that's 1, 0. Actually, I'm going to use a different colour because I want to make a particular point here. I'm going to draw the actual curve in blue. So, stationary point there, intercept there, that's 1, 0, this is 0, 0. So that's that part, I've drawn that. okay, included endpoints, etc. But then I also need to draw the graph of y equals 0 outside of that. It's really important. This happens frequently in exams, okay? You must make sure you actually draw in these parts. People often leave out the 0 part because it's sort of not really relevant, and it isn't. You know, there's no area under there, but it is an important part of the graph of this function. Okay, so make sure that you draw this part if it's part of the function. Okay. I haven't labelled the turning point. It's actually not really very relevant. Unless the question specified for me to label it, I probably wouldn't bother. It's going to take a bit of work to do it by hand. We could do it. We could get our cars to do it if we had it here, but we could also, you know, if we've got our cars, we could do a lot of things. So that's the derivative of that function, and so if I solve that, equal to 0 to get the turning points, so that's at 2/3. And then if I put 2/3 back into that, I should have defined it a bit quicker. 2/3 squared times 1 minus 2/3 is 1/3. I'm just going to type that. So 16 on 9. Okay, but I would say that, you know, unless it specifies, I wouldn't bother labelling that point. Okay, the second part is to show that f is a probability density function. Okay, so what I need to do to show that it's a probability density function, is make sure that it meets these two criteria. So having sketched the graph, I can see that the whole graph is on or above the x-axis for all x values. The second thing is that I want to show that the total area is 1. Now, I'm actually just going to pause and edit this graph just to give myself a bit more space here. Okay, I've just erased the excess y-axis at the top and shifted the graph up. So what I need to do is I can see that the from the graph we can see that f of x is greater than or equal to 0 for all x, and then we also need to show that the total area is 1. So integrating from 0 to 1 will give us the total area. There's obviously no area outside here. Okay. So integrating from 0 to 1, the cubic, I'm going to need to expand that out in order to anti-differentiate it. So I'm going to do that. Oh, sorry, hold on one sec. So expanding it gives me 12x squared minus 12x cubed. Should have left a lot more space here for this question, apologies. So antiderivative is going to be 12x cubed on 3, so that's 4x cubed, minus 12x to the 4 on 4, so that's 3x to the 4 from 0 to 1. And so that is going to be subbing 1 in, gives me 4 minus 3, and substituting 0 gives me 0 minus 0. And so it is indeed 1. So from the graph, f of x is greater than or equal to 0 for all x, and we can also see the total area under f of x is 1, hence f of x is a probability density function. Okay, shade the region which represents probability of x less than 0.5. Okay, we already worked out that that was 2/3 there, alright, so 0.5 is going to be lower down than that. So x less than 0.5 would be this bit of region here. Whether it's less than or equal to doesn't really matter. So that purple area would be the shaded region which represents the probability that x is less than 0.5. And then part C, find the probability that x is less than 0.5. So we want to integrate this time. So the probability that x is less than 0.5 is equal to the integral from 0 to 0.5. I'm going to write half just for doing my manual calculations of our probability density function, which is 12x squared minus 12x cubed. So we've already done this integral once, so we at least know what the antiderivative is. It's 4x cubed minus 3x to the 4, and we're doing that from 0 to 1/2. And so we have 4 times 1/2 cubed minus 3 times 1/2 to the power of 4, take away 0 minus 0. I always, I consciously still do the zero substitution. I think it becomes easy to potentially forget about it, and there are times when, depending on the function, substituting 0 into the function doesn't give 0. So it's important to still sort of think through the full process of what needs to happen. Okay, so here we've got 4 times a half cubed is an eighth, minus 3 times a half to the power of 4 is 1/16. So whilst 4/8 simplifies really nicely to 1/2, 3/16 doesn't simplify at all, so I'm going to need a common denominator of 16ths. So I'm actually going to write, instead of 4/8, instead of simplifying it, I'm going to make it 8/16 minus 3/16, and so that simplifies to 5/16. So the probability that x is less than 0.5 is 5/16. Okay, example 2. Consider the random variable x with a probability density function f of x equals k times x minus 6 squared, where x is between 0 and 6. Find the constant k. Okay, so thinking about this function, that's a quadratic function to the right by 6. Okay, so that's it there. K is the dilation, so that's defining what this value up here would be, and we are talking about this being a probability density function just between 0 and 6, so just between this part of the function. Okay, and so we kind of need to work out, well, what value of k is going to make sure that this total area here is 1. Okay, alright, so finding the constant k, we know that the integral from 0 to 6 of this function, k times x minus 6 all squared dx, has to equal 1. Okay, so a couple of things here. In order to antidifferentiate, we could antidifferentiate in that form, but it's only a quadratic, so I'm going to expand it out. That's going to be easier. I can also think about this k as a constant, so it can come out of the integral, and then I can divide it over onto the other side, so I'm also going to do that. So I'm going to have integral from 0 to 6, expanding this out is x squared minus 12x plus 36, and that's going to be equal to 1 over k. Alright, so I can focus on the integral on the left-hand side, and then I can worry about solving for k later on. So just getting it out of the way over here is sort of helpful, I think. Antiderivative is x cubed on 3 minus 12x squared on 2, so 6x squared plus 36x. We're doing that from 0 to 6, and that equals 1 on k. 6 cubed is 216, minus 6 squared is 36 times 6 is 216, plus 36 times 6 is 216. It's essentially, they both essentially end up being 6 cubed. Take away, and if we put 0 into that, we'll have all zeros, and that equals 1 on k. Alright, so these are cancelling out, so we've just got 216 on 3 there, and that equals 1 on k, and so therefore taking the reciprocal of both sides, k will equal 3 over 216. And 3 over 216 should simplify, since 216 is 6 times 36. So therefore it's going to be, so if we think about 216, I know is 6 times 36 because it's 6 cubed. And so if I halve that to be 3, I double that to be 72. So it's 3 times 72. So therefore this is 1 on 72 is k. Find the probability that x is bigger than 4. Okay, so probability that x is bigger than 4 is going to be the integral from 4 to 6. Okay, so remember my function is essentially that. Okay, and so if we want the probability of x being bigger than 4, we're talking about finding that area there, so integrating the function from 4 to 6. Okay, integrating from 4 to 6, what's my function again? 1 on 72. Oops. 1 on 72 times x minus 6 all squared. Okay, again we can take that 1 on 72 out the front, and we can expand out, so we can do our antidifferentiation. So it is x squared minus 12x plus 36. And then it is 1 on 72 times, what did we decide that was? X cubed on 3 minus 6x squared plus 36x from 4 to 6. so 1 on 72. Just thinking it might actually be easier to do the integral without expanding. I'm not going to have such nasty substitution with this big 36. Let me go back again. Rather than expand, x minus 6 squared dx. So remember, integral of ax plus b to the n is going to be, remember we add 1 to the power and divide by that new power, but we also need to divide by a, the coefficient. Okay, so it essentially ends up being 1 over a times n plus 1 times ax plus b to the n plus 1. So, and plus c obviously, but we're doing a definite integral. So in this case, that's going to be 1 over a is just 1, and n plus 1 will be 3, x minus 6 to the 3, from 4 to 6. So actually it's going to be easier, it probably would have been easier to leave it unexpanded up the top there when I did that integration as well. So again, you know, good maths is all about being flexible with the methods. So 1/3 times x minus 6 cubed from 4 to 6. Alright, so we've got 1 on 72. We're going to have 1/3 times 6 minus 6 cubed. Take away 1/3 times 6 minus 4, sorry, 4 minus 6 cubed. Alright, so 1 on 72. This is just going to be 0. Minus, here we're going to have 1/3 times, that's negative 2 cubed. Negative 2 cubed is going to be negative 8. Oops. So we've got 1 on 72 times, it's negative times negative, so it's positive, 8/3. The 8 and the 72 cancel down because 8 goes into 72 9 times, and so that's going to be 1 on 9 times 1 on 3, and so 1 on 27. So that's because we're doing that. And so we have 1 on 27 is the probability of x being bigger than 4. So looking at my diagram, thinking about the shape of the PDF, it makes sense that that's quite a small probability because we're getting sort of quite close to the x-axis there. Okay, so in most cases, as we've seen, probability density functions have restricted domains or a hybrid or piecewise functions. So we rarely have to actually calculate an integral from negative infinity to positive infinity. But there are some situations in which this is required, but wherever we can avoid it, we'll try to avoid it. So the integral from negative infinity to infinity can be found by evaluating the limit as k approaches infinity of negative k to k. And in fact, this is the mathematically correct way to write this statement. Given that infinity is sort of an idea of bigness, it can't actually be a limit of integration. You can't actually substitute infinity into something. So actually this is what we would write down. So as I've already said that, so while it's not actually mathematically correct to write that statement, if you have access to your CAS, when you integrate that, you type that in, you put infinity into the limits of integration, it will actually evaluate that. Note that when you're doing that, the infinity symbol can be accessed from the symbol palette or from the pi button. So down here we can click pi, there's an infinity there, or we can get it from the symbol palette, which is control book, where you've got all of the symbols available up there. Okay, so let's have a think about an example where we're going to need to integrate to infinity. Consider the probability density function with rule 2e to the negative 2x, where x is bigger than 0, and 0 where x is less than or equal to 0. So essentially this is a negative exponential going this way, but only for this bit here. So our probability density function is basically, sorry, it actually doesn't include that endpoint. In terms of actually sketching it properly, it's going to be that, and then that. Okay. So we need to show in part A, well, sketch the graph, sorry. I'll do it more precisely here. I didn't realise it was asking me to do that. And then we're going to need to show in part B that it's a probability density function. So we're going to need to show that this total area, which is an infinite area, is equal to 1. So we're going to need to integrate to infinity. So let me just do that graph sketch properly. We are going to need that y-intercept. So when x equals 0, this whole power will be 0, e to the 0 is 1, and so we're just going to get 2. So again, making sure you don't forget the y equals 0 section. It's part of the piecewise function. This is the point 0, 2. And other than that, we don't really need anything else. It's the origin, so we don't technically need to label it, but we may as well. Okay, show that f is a probability density function. So we're going to need to integrate from 0 to infinity. Okay, and mathematically that's not quite correct. So we're going to need to be taking the limit as k approaches infinity from 0 to k of our function, which was 2e to the negative 2x dx. Okay, so anti-differentiating an exponential. So we're still going to have the limit as k approaches infinity, so until we take that limit, it'll still be there. Anti-differentiating the exponentials, we're going to divide by negative 2, so 2 divided by negative 2 is going to be negative 1, so it's just going to be negative e to the negative 2x from 0 to k. So we're taking the limit as k approaches infinity. We're going to sub k in, so we're going to have negative e to the negative 2k minus negative e to the 0. And again, this is where I always do the 0 substitution, because that's not 0, that's 1. Okay, so limit as k approaches infinity of negative e to the negative 2k. I might write that as negative 1 over e to the 2k. Just helps me think through the limit. And then that's going to be plus an e to the 0 is 1. Okay, so as k approaches infinity, this power here approaches a really big number, gets bigger and bigger and bigger. Therefore, something to the power of a really big number is really, really, really big. And if we're taking 1 and dividing it by a super, super big number, that is approaching 0. Okay, so as the limit as k approaches infinity means that this whole thing will approach 0. Okay. Alright, so that means when we take the limit, we get negative 0, which is 0 plus 1, and so we're just going to get 1. And so therefore the total area under the curve, therefore total area equals 1, hence f is a PDF. And we can also see from the graph up above that the total graph is on or above the x-axis as well. Total area equals 1, and f of x is bigger than or equal to 0 for all x. Hence, f is a probability density function. Okay, now we know that it's a probability density function. We want to find the probability that x equals 0. Sorry, x is bigger than 1. Probability that x is bigger than 1. So going back up to our graph, the probability that x is bigger than 1 is going to be that area there. Okay? So that would mean integrating from 1 to infinity. So that would mean taking the limit as k approaches infinity from 1 to k of the function, which was 2e to the negative 2x. However, as I said earlier, we want to avoid having to integrate to infinity whenever we can. So the other way to do it would be instead to calculate that area and know that the probability that x is bigger than 1 is 1 minus this yellow area here. Okay. So the other way of doing that would be to say that it's 1 minus the integral from 0 to 1 of 2e to the minus 2x dx. And this is going to be an easier integral to calculate, especially with a limit of 1, one of the limits being 0. So 1 minus, antiderivative is negative e to the negative 2x from 0 to 1. Just be careful about the fact that you're subtracting, just keep everything in a bracket. So subbing in 1, we've got negative e to the negative 2. Take away, subbing in 0, negative e to the 0. So lots of negatives going on, so just be really careful about what's happening there. So that is going to be, that's positive 1. So I'm going to write it as 1 minus e to the negative 2. And so expanding out that bracket now with this negative here, because we're subtracting all of that, we've got 1 minus 1 plus e to the negative 2. And so therefore it is e to the negative 2, the probability that x is bigger than 1. Find the probability that x is less than 2 given that x is bigger than 1. Okay, so probability that x is less than 2 given that x is bigger than 1. So it's going to be this red area over the purple area. So we want probability that x is less than 2, given that x is bigger than 1, is the intersection of those two things, which is x being between 1 and 2, over the second thing, which we've already worked out in the previous question. So we just need to work that bit out first, so let's sort of do that separately. So we're going to need integral from 1 to 2 of our function, which is 2e to the negative 2x dx. So that is negative e to the negative 2x from 1 to 2. So that is negative e to the negative, negative 4 minus minus, so plus e to the negative 2. Okay, so that's what we can do with that. E to the minus 2 minus e to the minus 4. Alright, and so we've got e to the negative 2 minus e to the negative 4 over e to the negative 2. It does say to correct to 4 decimal places, so we can just put that in our cas, and in fact, therefore, we could have just done the integral in our cas. Sorry, I got ahead of myself. E to the negative 2 minus e to the negative 4 over, did this one say, no, it was exact up there, over e to the negative 2, control enter to 4 decimal places, that is 0.8647. Let's just check if we'd actually done the integrals, shift plus, integrating from 1 to 2 of 2 times e to the negative 2x, negative 2x, got the caps lock stuck on, let's try again, no, still got the caps lock on, okay, there we go, dx, over, we can do the whole thing, do the shift plus down here, that was, I'll show you with infinity, so 1 to infinity, if I put infinity in here, same function, so it might have been useful to define the function at the beginning. Let's try with the alpha keys at the moment, dx. Okay, so we're integrating from 1 to 2, so that's the probability that x is between 1 and 2 on the numerator, and dividing that by the integral from 1 to infinity, so that's the probability x is bigger than 1 on the denominator. Control enter, 0.8647. Okay. Alright, so the practice work for today is from exercise 15a.